Okay, today we'll be talking about simple harmonic motion again, and we're going to be using a reference circle to derive equations for displacement, velocity, and acceleration. So if we have a ball on a spring, and we displace it by a certain distance x, and let it go, there's a force pulling it back in towards its equilibrium. We'll overshoot the equilibrium, compressing the spring, and then therefore the spring will want to push it back out. It will overshoot the equilibrium again, and it won't want to come back in. It goes in and out like that. So if you plot this motion over time, by going in and out, it actually creates like this wave motion. So that's shape indicates simple harmonic motion. All right, so imagine we have a disc that rotates, and on the disc you have a ball. You shine lights onto the disc, and what you end up having is this ball going around and around like this, but as it goes around and around, it makes a shape on the film of a wave, indicative of simple harmonic motion. So we have the disc has to rotate at a constant angular speed, omega, and the ball casts a shadow. And the shadow is indicative of simple harmonic motion because it actually reveals the same type of pattern as we did before in the slide before. All right. The displacement of the ball in the x direction is the same as the displacement of the shadow on the screen. So if the ball is at this position here, the displacement is x, and which is also the maximum it can be, which we call that a. And as it goes around, let's say it's at this position, the shadow is at that position. So as the ball goes around and around, the shadow just goes back and forth like that. So the shadow will move from a maximum of a to a minimum of negative a. So we're going to actually try to use this idea to derive an equation for displacement. All right, so x is equal to a cosine of theta. So how did we get that? Well, here's a at some position, arbitrary position. And what we're trying to do is find the x value of a, which would be the same as a shadow. So this x value of a would just be a cosine of theta. So a cosine of theta would give the position of the ball, but it would also give the position of the shadow. And remember, the ball has to move at a constant angular speed, omega. And we know that omega is the change in displacement, angular displacement per unit of time. And remember that theta is equal to omega times t. So we can replace theta here with omega times t. And therefore we can actually come up with this equation, a cosine omega t. And whenever we use an equation like this, we've got to remember to always be in radians. So theta is measured in radians, omega is measured in radians per second. Okay? All right. Let's look at the graph of that shadow. The pattern repeats once every revolution of the disk. Okay, so it's going to go from some maximum value when it was on this side of the disk to a minimum value and then back up to a maximum value as it goes around the disk. So the shadow will do the same thing. The maximum value it displaces in each direction is called the amplitude. So you have a positive A or a negative A, it would be maximum. The time required to make one complete cycle is called the period. This shaded here area here shows it starting here and ending here, but it may be easier to look at it from this point of view. If you started at maximum amplitude, it will go down to a minimum amplitude and then back up to a maximum. So the time it takes to get from here all the way to here is a repeating of the cycle. So that's one period. Frequency, on the other hand, is the number of cycles that happen per second. and that's measured in hertz. And hertz is just a fancy name for 1/seconds. So frequency and period are reciprocals of each other. All right. We know that x is equal to a cosine of omega t. But we also know that omega is equal to theta per unit time, or angular displacement per unit time. And for one complete revolution, we know that theta has to be 2 pi, and time has to be period, because that's what period is, how long it takes to go around once. So we can actually replace omega, with 2 pi over period times t. But we also know that f, or frequency, is equal to the reciprocal of period. So we can actually either write it as a cosine omega t, or we can put in what omega is times t, or we can replace it with frequency in it, because we could either do 2 pi over period or 2 pi times frequency, because period and frequency are reciprocals of each other. All right. As I just stated before, omega is equal to 2 pi f, or 2 pi over period. Since angular speed omega is directly proportional to the frequency, as f goes up, so is the angular speed, or the speed goes up as f goes up. Sometimes we actually call this angular speed the angular frequency. And this is the form of the equation that you'll find in your AP formula sheet. You'll find this form of it. But there's a couple different formats that we can use. We can write it out the simple way. We can write it out using period instead of frequency, or we can write it out using frequency. All right, now let's try to derive an equation for velocity. Okay, first of all, hopefully you can see that the velocity tangential is the velocity of the ball at an instant that it wants to fly off at a tangent. We've talked about that before. And the velocity x is the same as the velocity of the shadow, and it's in the negative direction. But what is more interesting is the idea of this angle, and this angle are all equal. And using basic geometry, you can see that. Okay, so now that you understand the diagram, let's see what we can do with it. So we're going to use the same type of logic to derive an equation for velocity of the shadow in the x direction. Once again, we noted that the velocity tangential is shown in the diagram, and the velocity in the x is moving in the negative direction. So therefore, we have velocity of the x is equal to negative, because it's moving in the negative direction, velocity tangential sine of theta. Why sine? Because the velocity of the x is the opposite side of theta. So we want this velocity here, it would be the sine. Alright, so now we can do some substitutions with this as well. But we know velocity tangential is equal to r omega, because when you convert from linear terms to angular terms, this is the conversion of velocity tangential, or velocity linear, would be equal to r omega. And r, in this case, which is the radius basically, is equal to a. So therefore we have velocity tangential can be replaced with a omega. So there we have this equation. So now we replaced negative velocity tangential with negative a omega, sine of theta. But we know that theta is equal to omega times t, just like we did last time. So therefore we can replace this equation with negative velocity tangential, because it's going in the negative direction, is equal to sine times theta, or we can write it out this way. All right. Now acceleration. Now acceleration that the object would feel going around a circle at a constant speed would only be the centripetal acceleration, or the center-seeking acceleration. And once again, if we're trying to find the acceleration of the shadow, it would be equal to the x direction. So we're going to use the same type of logic to find out the acceleration of the shadow, which it would be the acceleration of the ball in the x direction. A sub c is shown on the diagram, and once again notice that the a and the x is moving in the negative direction. Alright, so we can actually write an equation for the acceleration of the x, which would be equal to negative ac cosine of theta. Why cosine? Because a of x is the cosine of the acceleration centripetal. And now we're going to do some more substitutions again. There's our equation we just derived. All right, but we also know that acceleration centripetal is equal to v squared over r, or v tangential squared over r. And we know that v is equal to r omega from the prior slides. And if we square that, it would become r squared omega squared. One of the r's would drop out, and you'd be just left with r omega squared. So we can replace this acceleration centripetal with negative r omega squared. And once again, we can do a substitution for theta as well, because theta is equal to omega times t. And there we have our equation for acceleration of the x. All right, let's try to summarize this because it's a little confusing, isn't it? The displacement is equal to a cosine omega t. So what is the maximum displacement? Just plain a. So if this whole end of the equation ends up being 1, then x is this maximum x is equal to a, which is the biggest it can be. Velocity, on the other hand, we had it negative because it was moving in the negative direction compared to the displacement, is equal to negative vt sine omega t. And we found out that we could replace vt with a omega and omega t, sine of omega t. So what would be the maximum velocity in the x? Well, when the term sine omega t is 1, we'd end up with velocity max is equal to the max velocity tangential, or omega times a, or a omega. Acceleration, the same type of thing. Here's the original equation we started with. We made some substitutions, right? And what would the maximum acceleration be? Well, the maximum acceleration would be when it's all the acceleration, and that would be a omega squared. And I left out the negative signs on both these because I was actually just thinking about the magnitude, not the direction on both these maximums. So let's look at this a little closer. So how in the heck are you supposed to remember things like this? Because only this equation, or a form of this equation, is on the formula sheet. Well, think of it this way. Look at the differences here. You go from cosine to sine to cosine again. Just remember that. Cosine, sine, cosine. And you go from a to aw, or a omega, to a omega squared, and everything else is the same. Okay? So if you can remember that, that would be helpful. And remember, all terms must be in radians. And also that this omega here really can be written as 2 pi f, or 2 pi over period. Okay? All right, so let's try a problem. We have a speaker, and we want to know the maximum speed of the speaker, and where does this maximum speed occur? So obviously the speaker is moving in and out, and we want to know where the maximum speed would be and what this maximum speed is. Some things note that this frequency is in kilohertz. So we need to first convert that into hertz. And this is in millimeters, the amplitude. We have to convert that into meters. All right, so we're going to find the velocity by using our equation. And we want to find out what the maximum velocity is. So this whole part of the equation here we don't really care about. All right. So we know that it's minus a omega, but we know that omega is equal to 2 pi f, and we're given f, and we're given a, so we just put the numbers in, right? And make sure that we put this in meters and this in hertz, not kilohertz. So the maximum speed is 1.3 meters per second. And the maximum speed has to occur midway between the ends of motion. Think of it logically. The whole time it's on this side, it's being accelerated back this way. The whole time it's on this side, it's being accelerated back this way. So where does it reach maximum speed? Right in the middle. Okay? That's it.